Cameron Landers. Thanks for watching. In our top 3 tools video, we provided a high-level introduction to equalizers. In this video, we'll do a more detailed discussion on when to use equalization, why and how to use it, specific tasks and strategies professional sound engineers use when applying equalization. As discussed previously, equalizers are used to boost or cut frequency ranges within the human audible sound spectrum. Equalizers can change the natural sound of vocals and instruments being recorded or performed in the studio or in a live setting. The sound produced by each type of instrument or vocal lies within a specific range of frequencies in the sound spectrum. The objective when using an equalizer is to isolate the specific vocal or instrument being performed, to bring it out or clarify specific instruments or vocals relative to others in the overall mix. As I mentioned in my top 3 tools video, equalization should seldom be used to boost frequencies. Rather, engineers should focus equalization on limiting unwanted frequencies. An engineer may choose to use a software-based feature or a plug-in within their digital audio workstation, or they may use a hardware-based device. Most digital audio workstation software includes some form of equalization, and software plug-ins are widely available. Beginners in sound engineering may not fully understand where in the signal chain to place an equalizer. Think of the signal chain as starting at the performance point, where the vocal is performed or where an instrument is being played. From there, the signal travels to the mixing console, either through a microphone or direct cable connection. Once a given signal enters the mixing console, it's captured on a specific mixer channel where its volume may be controlled using the fader, a sliding control for that channel. The basic job of a mixer is to use faders for each channel to mix all the input sounds together to create the optimum mix as heard by the audience as they listen to the final mix of the performance through the system's main speakers. A sound engineer may choose to implement any number of other processes on the signal as it passes through the mixer. One of these processes is equalization. Often, multiple different processes are used on a signal. Examples of processes that may be used include equalization, compression, reverbs, delay, and other sound effects. This routing of an incoming sound through various processes is known as a signal chain. One must consider the order in which these processes are applied to the signal. The order does matter. Typically, equalization should be the first process added to the signal chain before any sound effects or other processing comes into play. It's important to note that each process applied along the way affects all those that come later in the signal chain. This is particularly important when adding a sound effects such as chorus, reverbs, delay, and other such sound effects. For a deep dive into sound effects and how to properly order them, please watch our sound effects video later in this series. With proper equalization, each instrument can occupy its own sonic space. Using equalization to separately isolate the frequency ranges for each vocal or instrument provides a significant increase in clarity between instruments and vocals in the overall mix. Some of the main benefits of equalization are: it helps distinguish each instrument in a performance. It helps vocals to stand out in the overall mix, minimizes the chance that any instrument or vocal part will end up getting muddled in the mix. If you aren't all that familiar with electronics, and I'm sure some of you may not be, you may not fully understand what frequency is or how it's measured. Here's a brief rundown on that. Frequency in electronics is measured in cycles per second. A term for the unit of frequency is hertz, named after the father of frequency, Heinrich Hertz. 1 hertz is equal to 1 cycle per second. You may be wondering what I mean by the term cycle. A single sound or note, when viewed on an oscilloscope, is shown visually as a repeating pattern. This pattern is known as a waveform. There are 3 fundamental types of waveforms that we see on an oscilloscope. The first one looks like a sideways S. The S curve is known as a sine wave. The other two fundamental types of waveforms are sawtooth wave and square wave. I refer to these waveform types as fundamental because an actual sound's waveform is usually some combination of these basic patterns. For example, a note played on a trumpet or flugelhorn will generate more of a sawtooth waveform, has a sharp peak, while a note played on a clarinet generates more of a square wave. On an oscilloscope, a waveform is shown as a pattern of repeating peaks and valleys. One full repetition from the beginning of one peak and valley instance to another within a waveform's pattern is known as a cycle. Frequency is simply the number of these cycles that appear over time on the oscilloscope for a given note or sound. Time is measured in seconds, so we say frequency is the number of cycles per second. Audibly, frequency has a direct relationship to pitch. Higher pitched notes have higher frequencies, while lower pitched notes have lower frequencies. The oscilloscope displays cycles over time. A higher pitched waveform will show its peaks and valleys very close together, more cycles per second, while the lower pitched sounds will be displayed with peaks and valleys more spread out over time, fewer cycles per second. If you intend to operate an equalizer, you'll need to have at least some rough idea where the frequencies are for a given instrument or vocal. On an equalizer, frequencies are grouped into bands. Each band, or group of bands, is adjusted by a separate slider or fader on the equalizer. You need to know the frequency range of a given instrument to determine which bands on the equalizer apply to that instrument. You can then adjust it based on what you're hearing. The actual frequency range for any given instrument varies between different types or even models of a given instrument. For example, a trumpet and a flugelhorn will have different frequency ranges even though there are very similar spaces in the sound spectrum, and their wave forms are similar. An upright bass and an electric bass will be in slightly different ranges as well. A flute and a clarinet, even though both form mostly square waveforms, their frequency ranges will slightly differ. Each instrument lives in a frequency range somewhere. In equalization, your job is to find it. To do so, you can use a general guideline for well-known frequency ranges for different instruments as a starting point. Just know that any guideline is going to be very generalized and you'll need to tweak it based on your actual scenario. As a bonus for watching my video series, I have a handy frequency guide that defines all the general frequency ranges for every common instrument type. In addition to just the basic frequency ranges, this guide also includes frequencies where various additional characteristics such as complex characteristics of the attack and other such considerations. I've placed a link to this guide in the description of this video so you can download it from my website. I'll briefly summarize it here. Up in the higher frequency ranges, around 5 kilohertz and above, you'll find things like vocal sibilants, cymbals, chimes, the presence effect of acoustic guitars, the snap aspect of a snare drum, and certain other percussive instruments. The bulk of the sound vocals produce will live somewhere around the 1 kilohertz range. With that said, there are many aspects to consider when equalizing vocals. Vocal ranges may be anywhere from bass to soprano, so 1 kHz is only a general rule for bringing out vocals. As I mentioned, the sibilance characteristic of vocals lives up in the 5K range, and the air characteristic on that vocal will be more like 10K. Some of the richness of a vocal's mid-range sound may be found around 240 to 500 Hz. If a vocal sounds muddy, you'll usually want to cut somewhere around the 250 Hz range. My sound frequency guide explains these kinds of handy tips. If I'm hearing this problem, which frequency should I cut? It's a whole body of experience-based knowledge that I've accumulated and put into this guide over the years. So make sure and check it out. It's a very handy tool. Electric guitars are generally found in the ranges of 250 to 400 Hertz, depending on the material, the type of guitar, effects, and a host of other considerations. Acoustic guitars have additional aspects, such as the snap or the pluck or the pick within the attack portion of the sound, which lies somewhere around 5K. Particularly for guitars with nylon or catgut strings, that flappy sound of an electric guitar using an acoustic sim is found in that range as well. The fullness of acoustic guitar chords lives around 80 Hertz, while the body of the sound is at around 240 Hertz. Electric guitar chord or mid-range fullness may be found somewhere around the 240 to 500 Hertz range. Its presence lives at around 1.5 to 2.5 kHz. And if you want to bring out that 4x12 cabinet sound, make a slight cut at 1K. For keyboards, it depends on the patch. For organ sounds, you'll find fullness at around 80 Hertz, body at 240 Hertz, and presence at 2 to 5 kHz. Piano is roughly the same as organ. The honky-tonk style piano, though, has presence at around 2.5 kHz. String sounds have fullness at around 240 Hertz, and a scratchy characteristic like the bow attack on a violin at around 7 to 10K. With modern synthesizers, there are way too many different patches to characterize, so start with the organ guidelines and tweak from there. Horns have their own characteristics. Their fullness is around 120 to 240 Hertz, with a high-end attack characteristic around 5K. Bass guitar tends to live somewhere between 50 and 80 Hertz. I generally start around 80 Hertz and tweak from there to protect its sonic space from the low organs and the kick drum. Bass also has attack characteristics at about 700 Hertz, and the snap of the plucked or picked strings at around 2.5K. The kick drum generally resides around 50 Hertz. The hollow portion of that drum is at about 400 Hertz, and the baton attack at around 3 to 5 kilohertz. The snare's snap attack is up around 10K, crispness at 5K, boing sounds at around 900 Hertz, and you'll find the main fatness at around 120 to 240 Hertz. The floor tom has fullness around 80 to 120 Hertz, attack at 5K. Other toms have fullness around 240 to 500 Hertz, attack around 5 to 7K. Cymbals and hi-hats clang at 200 Hertz, sparkle around 8 to 10K. Again, check out my guide for this and a whole bunch of other useful details, tips, and techniques. It'll boost you up to the big-time expert level on frequency ranges. That's our deep dive on equalization. Please check out all our other great videos in the series. Please give this video a like and click that subscribe button if you haven't already. Thanks for watching, and I'll see you in the next video.